This lecture is meant to be a continuation of the lecture on superposition. And what I really wanted to talk about is to get you guys starting to understand how we can go from calculating the electric force from a bunch of point charges to a continuous charge distribution, which is what we're going to do next. So we're going to go to what the book calls, right, the general problem. And this kind of is the general problem in electrostatics. You've got some object. I'm going to call this a funky charge object because we don't want to really say anything specific about it. Okay, so we'll call that funky charge object FCO. Okay, it's got some charge Q. Okay. And now instead of a point charge, this object is our source charge. So, you know, maybe it's a spacecraft, maybe it's a sock, right, from the dryer or something like that. But it's some object that has acquired a charge. And practically speaking, this is what we want to understand. We want to understand what is the force from that funky charge object on Q. Okay, so what... This is a more general problem. Force does FCO, okay, exert on our test charge Q. All right, that's our question. Okay, so there's a couple of different ways, right, in reality that we can simplify this problem. If I've got a weirdly charged object, no matter what size or shape it is, but I pull Q, my test charge, really far away from that funky charge object. So this is if our funky charge object and Q are far away from one another. Okay. Our funky charge object is going to start looking like a point charge. It's going to get small, right, in perspective, and you can treat it like a point charge because it's going to, all the charge that might be distributed throughout it, it's going to act like it's basically concentrated at a single point. Okay, so you can treat our FCO like a point, okay, charge. Okay. On the other hand, if they're not far away from each other, our choice is a little bit different, okay? So we've got some object here. It's got some charge distributed around it. What I can do instead is I can take my funky charge object and imagine breaking it into a bunch of little charged objects, small enough. Okay, so maybe one part of this is more charged than the other, but if I break this up into small enough chunks, these little chunks are going to have the same charge. Okay, so this is another option. I can break my funky charge object into little chunks of charge, okay? And then I can treat each of these point charges each of these, getting ahead of myself, treat each chunk of charge like a point charge. And then I can do my vector addition, okay, just like we did on the lecture of superposition. Okay, so I can treat, so I've got my Q here, over here to the side. Okay, each one of these little chunks of charge, right, is going to exert some different force, and I can add up all of those forces together. Okay, for a real object, right, I might need to break it up into, I don't know, 1,000, maybe 1,000,000 pieces to do this well. Okay, this can be really tedious to do by hand. Okay, obviously. I will show you guys briefly. It's not necessarily tedious for a computer to do this. So an object that you guys might care about understanding the the charge of, or the electric field around, could be a spacecraft. Spacecraft get charged because they actually go through regions of radiation or regions of charged gases in space, and so they acquire a charge, which can have some bad effects on the electronics. So all of the spacecraft in space, the charging of that spacecraft is modeled and understood. So if you have a computer, you can take something like a spacecraft and break it into a grid, bunch of little pieces, assign some properties to that grid, which will determine the charge that it acquires, and then you can just do this vector addition, or the computer really does it, everywhere in space in order to figure out the electric field. Computers can do this pretty quickly by hand. Not so easy, okay? It's not totally doable, just tedious, okay? It would take a lot of work. All right, so in this class, we're not going to do a lot of that kind of coding, okay? Instead, we're going to do what the early people that derived electromagnetic theory did, okay? They made these chunks infinitesimally small. Okay, infinitesimally small. If you have then a kind of nice continuous charge distribution of an object, say something that could be described by an equation, then you can transform our sum, our vector sum version of Coulomb's law into an integral, and you're going to use calculus, right, instead of manually doing this vector sum to figure out the point or the force at a particular point. Okay, so that's kind of where we're heading. Okay, so I want you to imagine our funky charge object. It could be modeled as a bunch of little point charges distributed in three-dimensional space or two-dimensional space, remember, depending on the problem. In this class, though, instead of learning how to program it on a computer, we're going to say it has a nice continuous charge distribution throughout some kind of easier shapes, rings, spheres, boxes, and we're going to be able to solve the problem using calculus.